Hello YouTubers. Today we are going to look into selective harmonic elimination. This topic will be covered in two parts. In the first part, we will cover the theoretical portion which includes programming and simulation. In the second part we will cover the practical aspect of the topic. As per Fourier analysis, any periodic function can be expressed as a sum of trigonometric functions given by this equation. This gives the average DC value of the signal. Sine and cosine coefficients are derived using these two expressions. Let us consider this pulsating square waveform having frequency of 50 Hz. This is a non-sinusoidal waveform and can be approximated using a fundamental voltage waveform of 50 Hz and other waveforms having frequency equal to even or odd multiples of the fundamental frequency. The same information can be shown in a graphical format. The y-axis represents the magnitude and the x-axis represents the harmonic order. The first one is the fundamental component at 50 Hz. This harmonic component has frequency equal to 3 times the fundamental frequency, that is 150 Hz, and is called the third harmonic voltage. This is the fifth harmonic voltage. This is the seventh harmonic voltage, and so on. Now our aim is to remove the unwanted harmonics and try to control the fundamental voltage. Before we move any further, let us quickly discuss about the waveform symmetries. The presence of the even or odd harmonics directly depends on the symmetrical properties. The first one is half-wave symmetry. This is the condition for half-wave symmetry, which means any waveform which is inverted, symmetric about 180 degrees. So any waveform which satisfies this condition, confirms the absence of cosine coefficient DC component, and also the even harmonics from the sine terms. The second one is three-phase symmetry. To achieve three-phase symmetry, the inverter legs should be operated in such a way that the output voltage waveforms has phase difference of 120 degrees. Three-phase symmetry confirms the absence of third harmonics and its multiples, that is N3, N9, N15 and so on. Therefore we need to focus on the elimination of 5th, 7th, 11th and so on harmonic voltages. Now instead of this fixed square waveform, if we introduce notches like this, we can control the voltage magnitude and also remove harmonics. As per the selective harmonic elimination method, the number of unwanted harmonics which can be removed is equal to the number of switching angles minus 1. One switching angle is reserved to control the fundamental voltage. Therefore by adjusting the two switching angle values, alpha 1 and alpha 2 within 90 degree span, we will be able to control the fundamental voltage and only eliminate fifth harmonic voltage. To find the value of switching angles as per selective harmonic elimination, we need to write a program in Matlab. Here we have written an objective function to eliminate fifth harmonic voltage. We set the lower and upper bounds for the solution. We are using f-min function to calculate alpha 1 and alpha 2. You can also try using other algorithms such as Newton-Raphson, genetic algorithms, particle swarm optimization, resultant theory methods and so on. We also write this constraint function to regulate the fundamental voltage. Then we calculate the value of modulation index. Here we store the switching angle values in these arrays. For every iteration loop, we change the value of modulation index by 0.01. So let's run the program and we have the graph for switching angles alpha 1, alpha 2 with respect to the modulation index. Let us now copy these values in an Excel worksheet and select two sets of values for testing later. So here we have the values for modulation index, alpha 1 and alpha 2. And we select two solution sets, set 1 and set 2 for testing. Now this is a Simulink model where we can test the values obtained from the program. We give the input values for alpha 1 and alpha 2. These blocks generates the reference signals for phase R, Y and B with 120 degrees phase difference. These signals are given as input to the respective switching subsystems. Here we obtain the switching signals which are finally fed to the 3-phase, 2-level inverter model. Let's us check the output line voltage in the scope. Now open this Power GUI block. Select Tools and choose FFT Analysis. We can check that the fifth harmonic component is absent. Same observation is presented in data format also. Third harmonic is 0, fifth harmonic is 0 but seventh harmonic is non-zero. Let us check for the second set of values. Magnitude of the fundamental voltage has increased and the fifth harmonic voltage is 0. Join us in the next video where we try to confirm the simulation results with experiments using INV01 inverter module.